ml squared over 3. Okay. So one thing that I was thinking about when we switched to the center of mass as the moment of rotation, how we got from here to here. And so really, this is kind of like having two sticks sticking out in two different directions. But since it's symmetric, we can just add them up together. So this is like one stick sticking out of the one side with mass m over 2, and another stick sticking out of the other side with mass m over 2, and then the total length of each one being L over 2. And so, oh, sorry, I'm not lifting up my pen correctly. So just adding up those together, we can get m over 2 times L over 2 squared times 1/3. And then if we just add this together, then we get m over 8, m over 3 times 8, L squared. So that's ml squared over 24. And since there's 2, we can just add them together. Sorry, I'm times 2, this whole thing. And so this is m L squared over 12. And so that's just a different way of going through the algebra of getting the same answer of the same thing, just in case, you know. And so obviously this is smaller than the ml squared over 3 case. What? Okay, so this is smaller. This is smaller by a factor of 4. And that sort of gives you the power of what this x squared dependence means. So you see I got the same answer as Jack did without doing any calculus. This is obviously a little bit dangerous. You have to know exactly what you're doing. Calculus is sort of the surefire way of getting the right answer. And so my thought experiment was, okay, is this clear? Can I move on? Or is it still a little bit confusing? Okay, so my thought, the case of this disk that we just, you know, the way that you can think of it as something, some kind of stick, and you sweep it around. And the question is, like, why don't we get the same answer, ml squared over 12, as for this half case disk, or why do we get this answer of ml squared over 4?
Over 2.
Over 2, yeah. Or, okay. So even though, so the question is, we have this, oops. So the radius was, yeah, mr squared. So this is mr. Is it me?
Somebody walking in the
thinks that hear it. They're working on something on the roofs.
Okay.
Sound makes this huge.
Okay. So actually, I mean, why isn't it mr squared over 3? That's this question. Why is there the difference of mr squared over 3? So if this was just one rod that weighed m, then it would be mr squared over 3, because that's the original thing. But if you sweep it around in this circle, you get ml squared over 2. So what's the difference between sweeping just this rod and making a bunch of infinitesimal copies in a circle that all, and if you add all the copies, they equal m, versus just having a disk here? You know what I'm getting at?
Yeah, so I think what Nicole is saying is why, when you have this rod, you know, the moment of inertia, if you rotate about the end of the rod, is ml squared over 3. But when we have a disk, which you could almost think of as a bunch of rods next to each other, covering a full circle, why then does the moment of inertia change to ml squared over 2?
So it seems like it gets smaller if you have the rod but it's bigger if you have the disc. I don't know. Maybe I'll just leave it on the phone. I don't really want to answer.
Well, I mean, you know, so this again gets back to this d theta element, right? Of the, you know, with the rod, you can have the same mass density from one end of the rod to the other. Whereas with a disc, you know, what's the effective area of the disc near the center of the disc compared to the outside edge of the disc? Is there more mass towards the end of the disc or towards the center of the disc? Yeah, I mean, there's much more disc towards the edge of the disc than there is in the center of the disc, right?
Yeah, the fact that it gets bigger means that there's more mass at the end because the x squared dependence is bigger.
Yeah, and well, not exponentially, but it's basically one way of thinking about this is the disk has effectively given you a non-uniform linear mass distribution if you decomposed it into a rod, in that you've shifted more of the mass towards the end of the rod than you have towards the center of the rod effectively. And so again, if you do that, you expect the moment of inertia to increase, which is exactly what happens when you go to a disk.
Yeah, so the difference between the disc and the rod is that with the disc you have these wedge shapes.
Yeah.
And so you're effectively adding wedge shapes together. And
It
it,
wasn't one dimensional.
yeah,
Right, yeah.
and if you
Right.
had rods like this that you were adding together, that means that you would have the same amount of mass in this inner circle as in this outer circle. And so it would have, it would weight all this stuff equally, and then you would get the same ml squared over 2 back out of it again. But in this case, we have less density. We have less mass in the inner circle than the outer circle. And so the outer circle has more mass, means ml x squared matters more, and so you get a bigger moment of inertia out of it.
Yeah, because like the dm isn't a function of, like, it's just on the rod it's the same, right, every time. But if you just go by r from the center and take a slice on the circle, it gets bigger and bigger.
Yes.
Yeah,
So
yeah.
you get a different DM.
And it's,
And that's what we got.
Yeah.
If you, is this gone?
Quickly.
Okay, so- Yeah, so you can see here of, you know, so basically in the case of the rod, when we had our one-dimensional integral, it was like x squared dx. And here, once we've reduced this to a one-dimensional integral, it's like r cubed dr. So instead of being squared, it's cubed. And so that's, you know, kind of when you've effectively boiled it down to a one-dimensional integral. And that's, again, just this wedge, you know, it's growing like r theta. So your effective one-dimensional mass density is like r. It's not uniform. So, and so I guess just one thing real quick to leave you with here at the end is, you know, on the AP test, are you going to have the time to derive all these moments of inertia for any of the problems there? No, probably not.
Unless it's the actual question.
Yeah, so at least for me, the way I think of some of these tools is so this tool, you know, it's useful for a test you have in class, to where you have a little more time, and if you know, Mr. McClure says, you know, what's you know, figure out for this disk rolling down a plane, and you say, you know, oh my gosh, I can't remember what the equation for the moment of inertia of a disk is. You know, I can't remember that it's mr squared over 2. And so even if you can't remember, you can use these tools to rederive what the moment of inertia is. And the same thing on the AP test. You know, say you get there, and you run through, and say like 2/3 of the problems you know pretty quickly, and you answer all those. And so you get to the end, and you have 20 minutes left, and you have, you know, 20 problems, and you're not going to finish all of them. But if you say, okay, you know, for this problem, I know I can rederive the moment of inertia. It'll take me a few minutes, but I can rederive it and get it right, and, you know, get this problem. And so that's maybe more the context to think about these things as far as the practical upshot for test taking.
Yeah, so that's where it's good to have the mnemonics. So let's say I have a string with the ball at the end of the string. The mass of the ball is m. That's mr squared. A disk, mr squared over 2. A rod, mr squared over 3.
Yeah, just right.
Yeah. Yeah.
Okay, so yeah, make sure that you have your